the cloud. So this shouldn't take much time, hopefully, if I can find my, yes, this is not disconnect. Okay. So here's where we were in the morning session. We were speaking of data under specification. And what were the two mechanisms we discussed for handling data under specification? Anybody remember? Or model overfitting? Conversely, what were the two methods? Batch norm. Batch norm was not for regularization. What was it? Weight decay and deeper networks. Those were the two things that we spoke about, right? So weight decay was the regularization over here that we spoke of. And where we said that the network must be, that you want the network parameters to have low norm to ensure that the function doesn't rise too steeply, so that the model ends up learning a smoother function. And the other one, we said that if the model gets deeper, the function that it computes is more likely to be smooth than if the model is shallow, because a shallow network maybe has a little too much capacity for steep changes, right? Now, there have been other kinds of techniques proposed to improve the smoothness, L1 regularization, regularizing with added noise. But the one that's most interesting is called dropout. Now, how many of you are familiar with the concept of bagging? So that's one of you, two or three. So here is the general idea of bagging, right? Suppose I train many models for a particular classification task, each of them different, somewhat differently, and I take a vote over them. Do you expect the overall voted performance to be better or worse than the model performance for a single model? It's going to be better, right? So bagging is basically building on this simple concept. If you have a collection of training samples, what you would do is take different sets of randomly sampled different sets of training samples, train a model from each of them, and then you build a classifier from these different sets. And the actual performance model is going to be a vote over all of these different classifiers. And the idea is that if the classifiers are sufficiently diverse, the performance overall is going to be much better. Now, statistically speaking, what you would be doing is something like this. If I think of my model itself as this function h, where h is dependent on h is a function of these parameters, which is dependent on some training data, right? Then these parameters theta are going to be some function of the training set, but more generally, you can just think of these as parameters as some random set of samples from a distribution of parameters which give you roughly the same performance, right? And so in that case, I can have different models, h of theta 1, h of theta 2. I can have any number of models, or more generally, h of theta is your classifier, where theta itself comes from a probability distribution over parameters conditioned on some performance. And so the idea is that you want to take an expected value of h of theta as applied. So maybe the correct thing to do would be to say h of, let me write this as expected value of h of x semicolon theta, where the expectation is taken with respect to theta. And this is your bagged classifier. And the idea is that this is going to be give you better performance than any individual classifier which has only a single parameter. Is this making sense, guys? Questions? So why is what bad? So this is not just
the expected value of classifier. You just mentioned that it is bad.
No, I didn't say it was bad. I'm saying the exact opposite, right? What I'm saying is, suppose these are all the theta. So there isn't a unique setting theta that gives you a specific performance, right? If I give you a range of performances, if I say I want the performance to be between 97 and 98% accuracy, there's an entire distribution of theta values which will give you that performance, right?
Okay.
Correct?
Yeah.
And so when you train a model, you're picking one of these theta values, correct?
Yes.
What we are saying is that if I do something like this, h of, sorry, I'm typing carelessly. If I do something like this, where I say integral hx semicolon theta p theta d theta, right? Which is, I'm considering every possible value theta, right?
Yeah.
And weighting it with the probability. And this is simply the expectation of h of x semicolon theta. And the idea is that this is basically voting over all of these classifiers. And the idea is that if you vote over all of these classifiers, you'll end up with a better performance because they're likely to cancel each other's errors. Is that making sense?
Yeah. Yeah.
Right. Philip, did that make sense? They each, because they have a different parameter theta, right? So that is the general idea. I'm hand waving a bit. It's not exactly like that, but that is the concept we want to implement. So here's what we do in Dropout. During training, for each iteration, I'm going to turn off each neuron with some probability 1 minus alpha. So basically what I would do is, for each neuron, I'd have a coin, which has a probability of heads, alpha, and a probability of tails 1 minus alpha. And I'm going to flip the coin for every single neuron. And when it does that, it's going to switch off some of the neurons. And the resulting model is going to be something like this. So this making sense? Guys? Right. Okay. So this is what we want to do. So basically, we would have turned off some fraction 1 minus alpha of the neurons, right? And now, if I have a model which has, say, some n neurons, so I have a model of this kind, where the total number of neurons is n. I'm just drawing some subset of the connections, obviously, but I have a model of this kind, and then I have a total of n neurons. N in this case is going to be 4, 5, 6, 7. Of course, you're never going to switch off the output, 7, maybe even the input, 8, 9, 10, right? I have 10 neurons. So how many different ways do I have of switching off these neurons? Can you tell me? 2 raised to 10, right? I'm not 10C2. Where's the very 10, 2 raised to 10? So I can think of every one of these 2 raised to 10 combinations as a different model, can I not? So for example, if I have this very simple model where I have 3 neurons, 3 neurons, and 3 neurons, then this, so if I switch, here are different models I can derive from this. I can have this model, right? So it's only using these, that's one model. Here is another model, which is, I'm using just these lower two. I'm not, so this is not being used. This is not being used. I'm not showing all of the arrows. Here's another model where I use only maybe the 2 input features and these three guys. And that's one model. Again, all the arrows are not being shown, right? So here I'm not using this feature. So in this manner, by switching off different subsets of neurons, I can compose 2 raised to 10 possible different networks, right? Does that make sense? Right? And so when I'm using a coin flip to turn off neurons, what are you doing? I have 2 raised to n possible models, and I'm randomly sampling one of those models. Is that making sense? Right? And so that's what Dropout does. You're going to be It's not that you're going to just one of these models. Now, in reality, if you want to do a proper ensembling, you want to train all 2 raised to n possible models and take an average over all 2 raised to n possible models. And no, this is a uniform coin flip, so there is no bias, right? And in theory, you want to train all 2 raised to 10 possible models, and then you want to average your prediction across all 2 raised to 10 possible models. Correct? That making sense? Right? So in practice, it's going to be impossible to train all 2 raised to n possible models. So what will we do? We sample, right? You're going to randomly sample different subsets of those models in each iteration and update them, okay? And there's one common thing, that the weights are shared by all 2 raised to n possible models. So you don't actually have to see all 2 raised to n possible models to learn, at least to get an estimate for all 2 raised to n possible models. Is that making sense again? So what I mean by that is this one here. So if I have just this simple network, right? And then I have an output. This neuron is not considered. Then this guy has 1, 2, 3. Obviously, I can't. There are 2 possible models, 3 possible models. One model is this guy, correct? The other model is this guy. The third model is this guy. And this is the output. I have 3 possible models from this one common structure, right? You see what's happening here for this trivial model, right? Even if I train these 2 guys, I implicitly get this one because these edges are shared with this guy, right? Is that making sense? All 3 are derived from the same basic model. And so this gives us the benefit that you can actually sample from the 2 raised to n possible models and train those sampled models and still get, be able to compose any other model that you want. And so this is we basically switch it off. The output of the neuron is, it's like the neuron isn't there. So here, what if the sampling creates a bad model? You're training models, that's about it, period. So whether it creates a bad model or good model is not part of the question, right? So here's what happens. For the first training instance, I switch off some set of the neurons. For the second training instance, I switch off some other set of the neurons. For the third training instance, I switch off yet another set of the neurons. And in reality, for the 3 training samples, I'll be deriving 3 completely different models. So you see what is happening here? The black is off. I've switched it off, right? Now, this is in each iteration. Each time you're passing through the data, for each training instance, you're sampling a different model by switching off some random subset of neurons. And so in the next epoch, because the process of sampling is random, the same training instance may see a completely different model in the next epoch as you're going through the data. And now you're going to, so basically, the statistical interpretation is for a network with n neurons. There are 2 raised to n possible subnetworks obtained by choosing different subset of nodes, drop out samples over all 2 raised to n possible networks, and effectively learns a network that averages over all possible networks. So it is bagging. That clear? Anybody else? So if everything I've said so far made sense, please raise your hands, guys. It's okay. So basically, all we are doing is this: during training, you just keep randomly switching off neurons for each training data instance in each epoch, right? Now, why does this thing work? So it makes sense in terms of as a way of bagging, right? Of learning an ensemble of models all jointly by sampling the distribution of models. But there's a second interpretation. Dropout forces the neurons to learn rich and redundant patterns. Why is that? Think of a model of this kind, right? If I have a model of this kind, there is absolutely nothing, there is no constraint in your training process that doesn't simply have this first layer of neurons simply copy the previous output and all the rest of the weights become irrelevant. This is fully okay and fully possible within the standard paradigm, right? This guy over here. You see that this can happen. It may not happen to every neuron, but some neurons may just learn to copy the output of a different neuron. Can you see that happening? Right? Just totally randomly. It's a likely thing. But what happens as a result is that the effective model that you're left with is much smaller. You lose modeling capacity because through whatever vagaries of your optimization, some neurons simply learn to copy the output of a different neuron and didn't really do any job. By randomly switching off neurons, those neurons will sometimes, the ability of the neuron to simply copy gets eliminated because a neuron is able to copy things simply because the other neurons are taking over the load of the modeling. If you switched off the other neurons, then this neuron is forced to learn more rich patterns so that the overall network can model whatever it is you're trying to model. And so dropout also forces the neurons to learn denser patterns with redundancy. So these are the two behaviors of dropout. So how does it means that over here, basically, if you have subset of patterns in the lower layer, think about this. Let's say these are images and you're trying to recognize animals. It's okay for just this one guy to learn to recognize noses, right? But in the process of dropping out, there's always the likelihood that sometimes this guy will get dropped out. So now you're going to have multiple neurons learning to recognize noses. Does that make sense, Chirag? Right? So it forces redundancy in the representation as well. So how do you actually implement dropout? As you go through the training, for each neuron, you first flip a coin, which is a Bernoulli variable, with a probability alpha. If that comes out heads, then you set the mask value to 1. Otherwise, you set the mask value to 0. And then the output of every neuron is simply multiplied by the mask value. Afterwards, the rest of the operation is just as usual, right? So during training, how does this change things? During training, so does everybody see what the pseudocode is doing over here? For every neuron, I've flipped a Bernoulli variable to compute a mask. I'm simply multiplying the output of the network by the mask. So if the mask is 1, the neuron is retained. Otherwise, it's switched off. Do you see that, guys? Yeah. So easy enough, right? During the backward pass, what happens? During the backward pass, as you go backward, you would have basically computed the derivative when I say derivative I'm speaking of the derivative of the loss with respect to y, and from it, the derivative of the loss with respect to the z of the next layer. And then you have to push those derivatives back to the y's of the previous layer, right? That's what backpropagation does. And so here's what we are going to do. In your standard backpropagation, the derivative for any y was simply a weighted sum of the derivative of the next layer, right? Here, we are going to have the same term, except any term over here, this guy is going to be 0 if it was not used in the forward pass, and it's going to take this value if it was used in the backward pass. So basically, even during the backward pass, you simply multiply the derivatives by the mask. If it was not used in the forward pass, obviously its derivative is 0. If it was used in the forward pass, then the derivative is what it is. So is this making sense to you guys? right? So just raise your hands if the process made sense. Very easy, right? You compute a mask by flipping a Bernoulli variable in the forward pass. And then in the backward pass, you employ the same mask to compute the derivatives for the y's. That's it. When computing the derivatives for the y's, nothing changed. It's the simplest process in the world. Now, this is during training. How do you test? So during test, you have this issue. What we really want to do is here, any given network is going to be some function of in the input, and then neuron 1, neuron 2, all the neurons in the network. Or I can alternately write it as the network is a function of neuron 1 of X, neuron 2 of X, neuron N of X, where these are all the neurons in the network. So is this making sense? This notation, right? The output of the network depends on the outputs of the individual neurons. This clear? Right. So when I'm taking the expectation, so this is y of theta, which is for some specific combination of neurons, right? So if I'm taking the expectation of y, this is going to be the expectation of f of n1 of x, n2 of x, and so on, where the random variable is which subset of neurons was selected. This is what bagging would be doing, right? Is this making sense? Raise your hands if this is making sense. So the probability distribution over here is which subset of neurons was chosen, right? Because for each of the different 2 raised to n models, each of them chose a different subset of neurons, right? Okay, perfect. Except here is this thing. This guy is a humongously complicated model. The neural network is very, very complicated. So doing this expectation of f of n1, n2, dot, nn is not tractable. So we're going to approximate it. We are going to say this is a function of the expectation of n1, expectation of n2, and so on. Right? N is each neuron. Each n is a neuron. So, okay. So is this approximation making sense to you guys? Is this making sense? Yes, no. This is not Jensen's inequality. This is just an approximation. We are saying expectation of function of n can be approximated as function of expectation of n. This is not true. This is an approximation, right? Why is the second one more tractable? That's what we will see, right? So is everybody with me so far? Raise your hands if you are. Okay, so this is very easy, right? The rest is straightforward. So what happens here? Instead of saying the expectation of the network, I'm going to say the network of the expectations of the outputs of the individual neurons. What is the expectation of the output of the individual neuron? At the individual neuron level, each neuron is simply being turned on or off by multiplying it with a Bernoulli random variable, B, right? Which takes value 1 with probability alpha. This is for the individual neuron. So for the expectation of the individual neuron, it's simply going to be alpha times the actual value of the neuron itself. So you see how this math works. Do you see that, guys? If this made sense, raise your hands. Okay, so now, can someone of you tell me how you would implement this in inference time? How would you implement it at inference time? All you have to do Look at what is happening over here. So Mangalam, each neuron is undergoing this operation. You compute the regular output and then you multiply it by a Bernoulli variable with probability alpha, right? The only random variable is D. The expected value of D is alpha, correct?
Yes, yes.
So this is the expected value of the output of each neuron. So if I want to use the expected value of Y, all I have to do is to compute the regular value of Y, and what do I do?
Find the expectation.
How? I mean, guys, the equation is there staring at you. Somebody answer me.
So if we know the
probability.
Pardon me? Multiply by alpha, right? Madhav, this is alpha is just the probability of switching off the neuron for dropout. That's going to be the same through the network, right? So all you have to do is compute the Y for each neuron and simply multiply that by alpha, and that's it. That's going to give you your dropout network, inference using the dropout network, right? So what do you mean the forward neuron is dependent on backward? And what is a backward neuron?
So the neurons which are ahead in the layer, they would be dependent on the neurons that are on earlier layers, because if the earlier layers they get dropped out, the forward layers would be affected.
So that's besides the point, right? Here is what we said. Our point was this: if you want to do everything just right, you want to take an expectation, this expectation over here. You want to take this expectation here. Correct? This is where you're actually going to look at what happens individually across and how the neurons connect to one another, right? But instead, we are taking this, we are taking a function of the expectation of a function. We are saying is the function of expectations. That's it. Madhav, it's the expected value. During training, you are randomly switching on or off the neuron with a Bernoulli variable, right? Okay, Madhav, tell me this. If I flip a coin 100 times and the coin has probability alpha of being heads, what is your expected sum? What is the expected sum? 100 alpha, right? 100 times alpha. That's all we are doing. Here the output is F. The probability of selection is alpha. So it's going to be F times alpha or sigma times alpha. That's about it, right? So is this clear to everyone? Yeah. And so all we need to do to implement inference when the model has been trained using dropout is you have to multiply the output of every neuron by alpha. But there are a couple of different ways of doing it in actual implementation. If I think of any particular neuron with things coming in, it has outgoing weights, right? So instead of multiplying the output of the neuron by alpha, instead I can multiply all of these weights by alpha, correct? The outcome is the same, right? And so the second way to do it is to just say train your model and then multiply the model's W by alpha. Or what is commonly done is that during the forward pass, you multiply sigma, you scale down the neuron by the inverse of alpha. And during the far backward pass, and during training and during inference, you just use a regular network. All of these are exactly equivalent, right? So basically what you would do over here is on testing time, you're just going to, Y is going to be alpha times F. So is everybody clear with dropout? What happened here? Raise your hands if you got it. Right. So in terms of you might have, again, convergence is a different issue, timing, and you're right. So again, that's a bit empirical, so it's hard for me to say an explicit statement because sometimes the fact that the neurons end up learning more rich features can actually help you get to an optimum much faster. Okay. So here are some examples from Nitish Srivastava in 2013. This was on, I think, MNIST, and they showed how with dropout, it converges to a much lower error much quicker, right? So as you can see, timing in this case, it's actually faster. There are other variations on dropout. Instead of dropping out, you can say in recurrent neural networks that we'll see later, when you drop out a neuron, it stays dropped out throughout the input. Instead of switching off neurons, you can switch off connections. There are other things called shakeout, whiteout, various variants on the basic concept, but the concept remains exactly the same. So I suggest you take a look at these things in the net, and you might even try these in your homework. So any questions? Questions so far? None? Are there risks of dropout? It's not strictly beneficial. For example, if you do batch norm with dropout, it can hurt you, right? Dropout is this business of bagging. And there are situations where the whole hypothesis of sampling the distribution of classifiers may not work out in the way you expect it to. So there's always a bit of a heuristic. There are many problems where you shouldn't be using dropout. You'll find those out as we go through the course from your homeworks. Okay. So the story so far, the thing we've added is dropout is a stochastic data or model erasure method that sometimes forces the network to learn more robust models. So David, dropout is about, sampling the space of models, right? If you just apply to dropouts to some layers, then how many models are you left with? Is it 2 raised to n, or is it 2 raised to k, where k is the specific layer where you applied it, right? So if you restrict it to some layers, then the distribution of models is going to be over a smaller set, right?
So wouldn't that increase the computation time like exponentially?
No, it's just that for each training instance, you're just switching off things. That's it. And then you're as part of your forward pass, you're switching off some neurons. Nothing else changed, right? Right. So Manpreet, it's about thinking about the entire network as a sample, or this entire dropped out network as a sample from a distribution of 2 raised to n networks. So that you can even drop out inputs, right? The intuition is just that it's bagging. Okay. Now, there are a couple of other heuristics that I want to go through quickly because I have to leave, and I also don't want to keep you guys held up too long. Continued training can result in overfitting to training data. So you have things like you track performance in a validation set, and then when the performance in the validation set begins to go up, you can stop your training. This is early stopping. Also, this is very common. When you compute your gradients, your derivatives, your loss function is not always nice. And so there are occasions where the derivative will become too steep. And that can actually make your training unstable. So we often perform gradient clipping. We say if that the derivative is greater than 5 or some threshold, cap it at 5. This is a common trick we perform. Another common trick is data augmentation. Any amount of data that you get is going to be limited. So for example, I may give you a single picture of a Coca-Cola can. That's just one training instance. But then if I did all kinds of tricks to the same training instance, like rotated it by 40 degrees, flipped it, reflected it, it's still going to be the same Coca-Cola can, right? So I can create all of these synthetic training examples by manipulating my individual training instance, by distorting it, adding noise, stretching it, and so on, to create synthetic training examples that I can augment my training data with. This is called data augmentation, and it will generally improve performance, often in a very big way. You can in fact try this for your homework 1. Questions, guys? So I'm pretty sure that if you tried it for data augmentation on homework 1, your overall performance will improve. Any questions? Okay, so there are other tricks like normalizing the input, which you just performed in your model, initialization techniques. And in initialization, a key point is that neurons with identical connections that are identically initialized will never diverge. So you always need variety in your initialization. You can just perturb your MFCCs, add a little bit of noise to every MFCC component, for instance. Or you could go from the MFCC back to the spectrogram, add noise in the spectrogram, and then go back to MFCCs. There are various other things that you can do, right? You can stretch it in time, you can shrink it in time, things like that. Anyway, the point is, practice makes a man perfect. Your typical setting of problem is use appropriate representation for inputs and outputs, choose your network architecture, choose the appropriate divergence function, choose regularization, choose your heuristics, batch norm, dropout, etc. Choose your optimizer, perform a grid search for hyperparameters like learning rate, regularization parameters, etc. Maybe on a small, not held out data, but on a smaller training set, just so that you don't waste too much time. Train and evaluate periodically on validation data for early stopping if required. This is your overall process for training. So in closing, we've outlined the process of training neural networks. We've introduced some history, a variety of algorithms. We've looked at gradient descent techniques, regularization, convergence, heuristics. Beyond this, practice makes you perfect. So I'm going to stop here. Do we have any questions?